Okay, today's lesson is on logarithmic functions. Okay, so in previous, we know what with exponentials, we know what 2 squared is. It's 4, and 4 to the third is 64. However, when we have been presented this, as we did earlier in this unit, this is an exponential equation where you have a variable in the exponent. We have no way, or we've not learned how to solve this problem. You have not learned how to solve an exponential equation where the variable is in the exponent till now. In order to solve an exponential equation where the variable is in the exponent, we're going to use logarithms. Now, we did actually, let me sort of go back with this. We did actually, in the last couple sections, we did do this graphically. Remember, we sort of put y equals on this side and y equals on that side, graphed them, and then saw where they crossed. But you saw how tedious that kind of was, especially when they crossed in really, really large numbers, like 200,000. Or 50,000, you had to zoom out or make your window all big, and it just was so tedious. So what we have are logarithms to solve these types of equations. So if there is anything that you're going to remember or should remember in this entire notes, is a logarithm is an exponent. A logarithm is an exponent. A log is an exponent. So what we have here is the definition of a logarithm with base b. So it is denoted by this form here, the log of some expression equals x. Now we know how to solve this type of, we've seen this type of problem. B to some power, some number to some exponent equals some number. We did this the last couple sections. So we've seen this before. But what we haven't seen, and so let me just sort of identify, the B stands for the base, and then the X is the exponent of this equation. Now what we haven't seen is this sort of log base B of y equals 8. But what you should notice is that the base that was in the exponent is the same b that's in the log. So the base of the exponent is actually the base of the log. So how this is written, or how you would say this, is log base b of y is x. So you can see it down here, log base b of y equals x. And this is what I'm talking about. This whole expression, this whole log expression equals x. And over here, x is the exponent. So this is what we talk about. A logarithm is an exponent. This log is the exponent, okay, of our exponential. Okay. So when we go to write these, the whole purpose of using logs is to help us solve exponential equations. So it's going to be important to be able to understand the relationship between the log and the exponent. And the relationship is how we can manipulate the exponential to be a log. So you see the b base, x, exponent x over here of y. So how we do this is, if we go here and we say, okay, now we're going to change this exponential equation, or exponential probably sort of expression, into logarithmic form, you first start with log. Obviously, you're going to write log. And then what you're going to do, and this is sort of an important piece here, is start with the base. Then go counterclockwise. CC, counterclockwise. Okay, so what we do to change this, so if we notice the base of our log is the base of the exponent. So our base of our log will be the base of the exponent. So log base 5 of y, which ends up being what this is equal to, 125, equals the exponent, because a log is an exponent. A log is an exponent. So one way to sort of remember this is when you're going from exponent form to log form, start with your base, then go to what it's equal to, and then back to the exponent, counterclockwise. Log base 5 of 125 equals 3. So what this reads is log base 5 of 125 equals 3. Then we can go the other way around too, and it's the same thing. Okay, so we start with the base. Remember, the base is the same. The base of an exponential and the base of a log are the same b. So when I'm going from a base of a log to an exponential, it's the same base. And then you work counterclockwise. 10 to the third equals 1,000. And hopefully that should make sense. It should 10 to the third. If you did 10 to the 1,000th equals 3, then that wouldn't make sense. Okay. So what I want you to do is practice this, and you're going to practice. You're going to fill this in. Take a few minutes. Okay. Do the counterclockwise. Start with your base. Move over, and then move over in a counterclockwise fashion. Okay. Notice here 5, 125, 3. 5, 125, 3. 10, 3,000. 10, 3,000. And go ahead and try these right here. Take a minute and do that. Okay. For the first one, changing it to log form, first we write log, then start with our base, 2. Same base. Base of exponent, base of log. Same thing. Move over counterclockwise, go to the 32, and then the exponent. A log is an exponent. A log is equal to an exponent. Okay. Here, again, start with the base. Go into exponential, the 12 will be our base. Same base. Counterclockwise means 12 to the 1 equals 12. Here, going to log form, write log, start with our base, same base, and work counterclockwise. Log 4 of 1 equals 0. Okay. Log is an exponent. Here, start with our base, 16, move counterclockwise to the 0.5 equals 4. Okay. A couple things that you may have come across that you might notice, maybe not, is the fact that we have a 0 exponent. What you should have learned in Algebra 1 and maybe a little bit here in Algebra 2 last semester is that anything to the 0 power is 1. So whenever you have a log base b of 1, it equals 0 because b to the 0 power is 1. And any base to the 0 power is 1. That means that any base log of 1 is 0. Based on our log properties, we know this. This is what we know. We know that anything to the 0 power is 1. But therefore, if we write it in log form, okay, log base b of 1 would equal 0, okay, using our log properties. Same thing goes here, and we sort of saw this right here. What we saw here, though, is if you notice that the log base number of the same number, so log base 12 of 12 is 1, and then that goes back to, we know this. We know this. We know that any base to the 1 power is the same thing as the base. So if we just use our log properties, that the base, so log of b equals 1. So anytime you have a log base that is the same as the number, so log base b of b, or log base 2 of 2, or log base 5 of 5, it's going to be 1. Because we know that based on our exponent properties, anything to the 1 powers itself, that's why you do that. So a couple things that we can use to evaluate here. So this is where we're going to, I sort of got off the screen there. One of the things here we're going to do here is learn to evaluate some of these. And this is where you're going to need your graphing calculator. So on our graphing calculator, let me just slide this over. Okay, we have a log button, and some of you have already noticed this. Let me sort of scoot this up so we can see this. Over here you have two different log buttons. You have a log, log log, and you have an ln log. This is a common log, and this is a natural log, which we'll discuss on the next page. But when you are calculating logs, you will use this log button. So when it says log base 4 of 64, we can evaluate that using logs. Now here's the problem. So when I push log, it doesn't allow me to put in the base. So that's one of the sort of drawbacks of the calculator. So logs, traditional logs, have a base 10 naturally. So if I push log, the button log on my calculator, it's going to assume a base 10. Now, well, here's the problem. Not all logs are base 10. As we can see here, we have log base 4, log base 5, and then we have log base 1/5 and log base 36. So, I mean, how do we change this? Well, this is different for different calculators. If you have a TI with the newer operating system, which I have here, you can type in a log of any base, and you don't use the log button here. What we do is we go to math, and we scroll all the way down to the bottom. Oop, too far. And what we see here is log base. What this does, if we click log base, is this allows us to change the log to the base that we need. So I can do log base 4 and then go over here of 64 and actually calculate this. Okay, and I get 3. But you're like, Mr. G, what if I don't? I have a Casio, or I have an older TI that doesn't have the newer operating system. How do we do this? Well, you're going to learn a little bit about this a little bit later, but why not introduce it now? So if you have an older calculator that doesn't allow you to type in the log as this is, you can change, you can do something that it means the same thing. So if you take the log of the bigger number and divide it by the log of the smaller number, you'll get the same answer. So what this means is if I do log of 64 divided by log of 4, I will get the same answer. I don't know if you can see that. It's kind of dim. Move it down. So notice how I did log of 64 divided by log of 4. So I can do the same thing in here. So if I do log of 64, remember I need to close parentheses, divided by log of 4, close parentheses, I get the same thing. So that's a workaround. If you have a newer calculator with a newer operating system, you can just type this in. If you go to math again, go down to the bottom, and you'll see log base, and then it allows me to put in whatever I want. But if you have a Casio or an older version of the TI, you're going to have to do this change. This is called a change of base formula. So it uses log base 10s to do the same thing. So if I log the big number divided by the log of the smaller number, I get the same answer. So same thing I can do here. So if I'm using an older calculator, this is a little bit, let's see if I can make this a little darker. There you go. if I do log of my bigger number, so 0.2, over log of my smaller number, I'll get the same answer. Log, so I'll show you here, log of 0.2 divided by log of 5, I get -1. So I should get -1. And now if I do the change of base method, so the newer calculators can do change base, log of 5 of 0.2, and we get the same thing. Okay. And you can even do fractions. So if we want to do fractions, and let me sort of bring the calculator over here. So if you have an older calculator, I would do log of the bigger number divided by log of the smaller number. Now, if you're going to type this in your calculator, just make sure it's in parentheses, 1 divided by 5, or you can just change it to a decimal, 0.2. So I can do log of 125 divided by log, and I can actually put in 1 divided by 5 and get -3. And if you have the newer calculator, you can put 1 divided by 5 in there. So I can do math log base, and I can actually do the base is 1 divided by 5 like that of 125 and get the same thing. Okay, and same thing here. If I do log of 36 divided by log, log of 6, I almost did that backwards. A log of 6 over log of 36. By bigger number, I mean like the actual physically, it's the bigger number. And log of 36 in the bottom. I get 0.5. So, that's that. Okay. So, evaluating common and natural logarithms. The common logarithm is a log that is used for our traditional exponential equations, and the common log is a logarithm with a base 10 of 10. So what this looks like is log base 10 of x. Now oftentimes you won't see log base 10 of x. A lot of times it'll just be written log of x. It will assume base 10. Much like you don't put 1 as a coefficient, like 1x, you don't need to put 1. It's just x. We assume that the coefficient is 1. So when you have log base 10 of x, when you see it as log of x, we assume that it is a base of 10, and that's what it is. If it's not base 10, it will have something else there. Like if the coefficient were 2, then there would be a 2 there. And the natural logarithm is a logarithm with a base e. And this is used for natural base e exponential equations. When you have an e in the exponential equation, you're going to use a natural logarithm. Now what that is a log that is base e of x. Now you will never see log base e of x. They actually write it as ln of x. But it is assumed that the base is e. Now why they call log base e of x ln x has to do something with the Latin origin of the words. But this is how you're going to see it. You're going to assume that the natural log is going to be ln and it is a base e. Okay. So we can evaluate with all of those. Now look at all of these. There is no base, so we can assume it to be 10. And when there is no base, we don't have to do a change of base. We can everyone, no matter what calculator you're using, can just do log of 8 equals. That's it. 0.903. So when there is a standard base, you don't have to do the change in base. Same thing with natural log, which is ln down here. It's ln 0.3 equals, and that's negative 1.220. And log of 16, same thing, log of 16, enter, 1.204. So when there is no base, then it assumes to be its natural base. Then you can just use the buttons log and natural log. You don't have to do the chains of base or anything. The last part here is the inverse properties of logs. And basically it states, and I'm not going to go into too much detail because I don't think that it's necessary, but basically you have to understand, much like addition cancels out subtraction and multiplication cancels out division, or vice versa, division cancels out multiplication, squaring cancels out square roots, cubing cancels out cube roots. The same thing, the inverse properties of logarithms are the same with exponential equations. So a log base equation here will actually cancel out an exponential equation of the same base. So if I have something that is 10 to the x, if I had a 10 to the log of the same base of x, they cancel out and my answer is just x. Or whatever the number is here. It could be anything. It could be 5, 10, 25, 2x, whatever. Whatever is here. If you have an exponent and you do a log of an exponent, actually, it's like squaring a square root. If I log an exponent of, if I put a log as an exponent of the same base, they cancel out. Same thing vice versa too. So if I have log, wow, that's a big log, log of 10 of 10x, so I have a log of an exponent where the bases match, and we already did this earlier. When the bases match, they cancel out, and my answer is just whatever is up there in the exponent. So we can see that example here, and let me zoom in. These are kind of small. So we can see this here, that 10, now because there is no log in between here, we assume that to be 10. So we have an exponent, a log is an exponent, same base, cancel out, and whatever's up there in the exponent is the answer. Now where it gets a little tricky is where these are not the same. Here I have an exponential and a base where the exponential and the base are not the same, 5 and 25. You have to think a little bit abstractly as to what 25 is. Well, if you understand that 25 is just 5 squared, we can substitute this back in and make this log 5 of 5 squared with the x up there as well. And now they have the same base. Cancel out. My answer is just 2x. Here, it's assumed that natural logs will have a base e. So I have a base e and a base e that'll cancel out. So my answer is 4. We'll be using these properties to solve equations later on. So it's important to understand that when you log something of the same base as the exponent, it cancels out and it just returns to x. Same thing as if I log an exponent of the same base or exponent a log of the same base. If they have the same base, they cancel out. Okay. If you have any questions, let me know. Otherwise, good luck.